Sammy and all the volunteers and everyone for planning this conference. I've had a great time so far, and I really do feel honored to speak here with you all. And the only thing that stands between you and lunch is a talk on compilers. So hopefully that won't be quite as bad as it sounds, because what I want to talk about today is the fact that compilers aren't magic. Okay, all right, let's try that again. Compilers aren't magic. All right, one more time. Compilers aren't magic. Oh, this looks promising. All right, so sorry about that. I just had to get that out of my system. I promise there won't be any more GIFs throughout the rest of this talk, but there will be continued gratuitous use of skeuomorphic keynote animations, so buckle in for that. In all seriousness, though, over the course of this talk, what we're going to do is convince ourselves that compilers aren't magic. Now, we're not going to live code a whole compiler up here. That would be a little too much to bite off, and I'm not as brave as Mohammed to live code up in front of all of you. But what we will do is break the seemingly daunting task of writing a compiler down into simple components. And any one of those components by itself is going to seem manageable, like something that we could build and implement. So a couple of them, in fact, are going to be what I would call sufficiently Stack Overflowable problems, which is to say that they're kind of like, run-of-the-mill programming challenges for which there are pretty good resources available online to work through those issues. Now, in a couple places, we will see some techniques that are perhaps non-obvious, but are readily understandable once examined. You don't have to be a wizard to understand these concepts. So when we look at those areas, we'll look at a lot of Swift code. I'm going to put it right up here on the screen on these slides. And in particular, there are a couple of places where I'm going to highlight where some of Swift's features make our implementation even simpler and cleaner than it would be otherwise. So by the end of the talk, the hope is that we'll all walk away feeling as if we could write our own compiler if we wanted to. We'll know that writing one isn't totally trivial, but it will seem doable and comprehensible rather than some kind of dark art. So let's start by asking a stupid question, which I've actually found is a pretty good way to get started on a lot of things. So here's a stupid question. What is a compiler? And very often, if you ask a stupid question, you get a stupid answer. So a compiler is a computer program. Now that may seem obvious, but how often do we think about it that way? That when we're in Xcode and we mash Command B, there's actually another computer program that someone else had to write that's running and doing some work for us. So there's actually an insight in here which is kind of important. Most of us build apps, and apps are just computer programs, and those programs run on little computers that happen to be in our pockets. So as long as we know how to write a computer program, we know enough to get started building a compiler. We don't have to first run off and learn C++ or assembly. We don't have to learn some dark, opaque theory. We can get started using the languages and the tools that we're used to. So let's do that. Let's build a compiler in Swift. We can do it right in Xcode by setting up a command line application that's going to run on our Mac. So we're writing an app, and that app just happens to be a compiler. Ooh. So the next obvious question to ask is, what do we want our compiler to do? So another obvious answer, we want it to compile stuff. But what does that word actually mean? Well, fundamentally, what a compiler does is it takes code in a language that the computer doesn't know how to execute, doesn't know anything about. And it translates that code into some other language that the computer, one way or the other, does know how to execute. So we call that the source language, the one we're writing our code in. And then the language that we output is the target language. And in between is the process of compilation. Now, we can define or think of code as just being a stream of characters conforming to some language definition. So again, when we're writing Swift in Xcode, what we're really doing is we're putting a bunch of bytes into a file somewhere. And those bytes are just characters that combine to conform to the rules of some language called Swift. But that language is really just an abstract concept, right? It's not something the computer knows anything about. And it's not until the compiler does its work do those instructions that we've expressed in this language called Swift get translated into something that the computer knows how to run. And again, that's called the target language. Now, the target language can be the assembly language of the specific processor where the program is going to run. And in fact, eventually, you're going to have to get there one way or another. But it doesn't have to be initially. The Swift compiler itself, for example, targets an intermediate representation called LLVM-IR. That's kind of a general purpose but low-level computer language. It's not assembly, and it itself is subsequently compiled by its own toolchain down into the assembly that runs on our Macs or on our iPhones. So there are real production compilers that target even higher level languages like C, and then rely on a C compiler to get down to something that runs on the machine. And there are even compilers, real compilers, that target interpreted languages, specifically JavaScript, and the reason that we do that is so that compiled code can run natively in the browser. So what have we learned just by thinking about our compiler as an app that we're going to build and trying to come up with some requirements for it? Well, we know that we're going to have to define some kind of source language, the one that we're compiling. We know that we're going to have to choose a target language that somehow the computer needs to know how to run, and we're going to generate instructions in that target language. So we're going to have to read in a stream of characters in our source language, probably from a file somewhere. Then we're going to have to break those characters into the language components of our source language, process the instructions that they're representing, that the developer is expressing, and finally generate instructions in this target language. Then we'll have to put those instructions somewhere, again, probably in a file, and do some kind of finalization step, maybe an intermediate build step. So let's get started by talking about the source language. So since this is our first compiler, and we get to decide what language we're writing, it makes sense to pick a language that is fairly straightforward to implement. We don't have to jump straight to implementing something like C, right, an ANSI compatible C compiler. And Bitsy is a little language that I developed while I was learning about this myself, and for this talk as well, preparing for this talk. And it aims to be the best language to implement when you're writing your first compiler. So I'll point you to a GitHub repo right here. This is a repo called Bitsy spec, and what that is a series of unit tests. It's a command line utility that you can run pointing at your implementation of a Bitsy compiler, and it will run code and see if your compiler is performing the way that is expected, or where there are places where you still have to fix up the implementation or implement additional things. So let's take a look at some sample Bitsy code. This is a very small Bitsy program that calculates the factorial of a given integer. And it's a good thing that we've chosen to calculate the factorial of an integer, because in Bitsy we have only one data type, which is the integer. So really simple limited language. That's kind of connoted here in the syntax as well. It kind of looks like maybe BASIC and Pascal got in a car crash a couple of decades ago or something. And so, you know, that's because this language isn't going to be the language that you write something that you're going to deploy to production in, right? It's really a toy language, but it's designed for learning about the process of language implementation and to make that more approachable. So I want to tell you a little bit about this language before we dive into implementing it. All Bitsy code has to go for a given program in one file, and in fact, all of your executable instructions have to go between two keywords, the begin keyword and the end keyword. And that end keyword is also going to be used to terminate other blocks throughout the language. There are comments in Bitsy, as you see. Those are block-style comments between curly braces. They can go anywhere in the file, and they can span multiple lines, but they're not nestable. Now, I said we have only integers in Bitsy, so obviously we have integer literals, and we have variables that can store integer data, and those variables can be named with any sequence of characters, or letter characters, or underscores. So we do assignment with the equals operator, and we do math using the same operators we're used to from other languages with the same precedence rules and parentheses. You see down in that else block, I've pulled out a -1, so I'm just doing x minus 1, but I pulled out the -1 to show you this all works like you're used to in other languages. We have a looping construct in Bitsy that you see there. That's the only loop construct we have, and it just repeats the block inside of it indefinitely until control flow reaches a break keyword, and break just exits the inner loop, so loops are nestable. We have a couple conditional statements in Bitsy. They're different than the ones that we have in other languages, and that's, again, because the only data type that we have is the integer. So we don't have Booleans. We don't have Boolean operators or Boolean logic at all. So we have these conditional statements, the first of which is if z. So if z takes an expression, and it evaluates that expression, and if the expression evaluates to 0, it performs the conditional block. And if it doesn't, then it will perform the else block, which is optional. That can also be there. Now, if p and if n work similarly, except with positive expression evaluations and negative expression evaluations, respectively. Finally, we have a little bit of I/O in Bitsy, the read keyword and the print keyword. So read takes a variable name, and it takes input on standard in, and it interprets that as an integer and loads it into the variable. And the print keyword evaluates an expression and prints the integer with a trailing new line to standard out. The other thing I'll note here is that variables don't have to be initialized in any way, and they're assumed to have a value of 0 before something is assigned to them. So that's it. That's the whole language. So we've gone ahead and we've completed our first step, which is defining our source language. Now we have to choose a target language. When we talked about the target language before, there was one requirement that we mentioned, which is that the computer needs to know how to run it. But there's actually another requirement implicit in here, which is that we need to know how to write it, and that's because we're going to be creating the compiler that emits code in this language. So what's a language that the computer knows how to run already, and that we all know how to write? So there's an obvious choice here, and it's Swift. And that's the language we're going to use. There may be some good reasons why Swift doesn't make a great compilation target in a, quote, real compiler, but it's a perfectly valid choice for learning about the process of language implementation here and the process of code generation. And in fact, if we can write real compilers that target JavaScript, I think anything is up for grabs at that point. So we've defined our source language, and we've chosen a target language, and now we know that we're going to have some Bitsy source code, probably in a file somewhere, and we're going to want to read that source code in, and we're going to want to kind of traverse over that code one character at a time. And this turns out to be one of those Stack Overflowable problems. So not totally trivial. In fact, there's some weird string stuff in Swift that you may not encounter if you're not used to working with, like, at the character level in Swift, but it's something that you could work through and find resources for. So now we get into the meat of the actual compilation process, and the first step here is to break those characters into the components of our source language. So we don't want to be operating throughout the whole process at the level of individual characters. That process has a fancy name. It's called tokenization. But again, it's really a simple concept. It's just this idea that we want to break the source code into meaningful chunks, which we'll call tokens, and then we just want to return a traversable list of these tokens. So what does that look like? Well, when you and I look at source code, we don't see it as individual characters. We see it more like this. So we don't see a B, an E, a G, an I, and an N. We see the begin keyword. We recognize that as one atomic unit, and it has some meaning to us, which is that the rest of our Bitsy code is about to be, the rest of our instructions are going to follow this keyword. And we do the same thing with variable names, right? We know that the same name in one place represents the same variable if we see that name in another place. We do that with integer literals and operators and comments, etc. So that's what we need to teach our compiler how to do. Let's start by implementing those little chunks, the tokens. And there are at least two pieces of data that we need our tokens to store. The first is the kind of language element that we're dealing with. So is this an integer literal? Is this a variable name? Is this a keyword, and which keyword is it? The second piece of data that we need to carry forward are the original raw characters, the original string from our source code that this token now represents. So let's look at this very simple Bitsy program, maybe the Bitsy equivalent of Hello World. And if we tokenized it, we would want to end up with something like this. So a traversable list of these little data structures, and each one carrying forward those two pieces of information. So look at the integer token, for example, in the middle there, that red box. It says, I'm an integer, and my value, the value that the developer typed when she wrote her Bitsy code, was 42. Because obviously, if we're going to be generating equivalent code in Swift, we're going to need to use that value at some point. So since we're dealing with Swift, and we're talking about an abstract type, we'll start with a protocol. And we said that we had to carry forward the kind of token that we're dealing with, or the type of token. And we'll use an enumerated type for that, and we'll back that enumerated type with a string raw value, and we'll see why that's important in just a little bit. We also said we had to carry forward the raw value in the source code, and we'll just use a string property for that on our token. So it turns out there are two classes of token that we need to broadly consider. One class is a token that has one type, one specific type, but that type can carry an arbitrary value. And the second class of token are those that have multiple types, but specific values. So let's look at them one at a time. So tokens that have one type but arbitrary values. So an example here would be an integer. So an integer is always just an integer. We can actually hard code that into our token, integer token struct. But the value of an integer token is arbitrary. It can be any string of digit characters. And so we'll just use a value string, we'll just use a string property here called value, and we'll let Swift give us an initializer for free. And note that we're not doing any validation here. We're not ensuring that the integer token is initialized with a string of digit characters only. So we'll have to handle that somewhere else in our compilation process. Now, variable tokens have an equivalent implementation. They're always variables, but they have arbitrary values. Any string of characters or underscores is valid. And whitespace tokens and comment tokens are going to have the same properties, and so they would have equivalent implementations. Now, the second class of token are those that have multiple types but specific values. So an example here would be a keyword. So think of the end keyword. The end keyword is always represented in Bitsy by END, all caps. So every end token is going to have that value. But there are more keywords than just the end token. There's the end keyword. There's begin, loop, the various conditional tokens, and IO keywords. So there's different types of keywords. And here's an implementation of that keyword. And what we're doing is we're taking advantage of this raw value that we backed our enumerated type with. So what we do is we expose an initializer, and we say, give us a string that represents a keyword. And we use that string to try to create a token type with that string as the raw value. And if that succeeds, then we know that we must be dealing with a keyword, right? It worked. And if it fails, there's really not much that we can do here, because the string that you've given us simply doesn't represent a keyword in the Bitsy language. So we use a failable initializer, and in that case, we return nil. Now, operators and parenthesis tokens are going to have equivalent implementations because they're also backed by a single literal string in the source code. So we've implemented these little data structures that we're going to use, the tokens. Now we need to talk about the tokenizer. This is the thing that's going to return that traversable list of these tiny data structures. So it's going to walk over the characters, the source characters that we provided, and return this stream of tokens. So here's the public interface for our tokenizer. It provides a property that allows us to peek at the current token, and it provides us with a method to advance to the next token. And internally, that advance method is just going to set the current token to the results of this private function called takeNext. And that takeNext function is going to do exactly what it sounds like. It's going to take the next sequence of characters and turn them into a token and return it. So implementing this takeNext function is really the meat of the tokenization process. So let's talk about tokenizing integer literals as a good place to start. If our tokenizer was looking at this program and came across the 4 character, we would want it to recognize that that 4 character belonged concatenated with the 2 character and that it was an integer token. So if we were going to formalize the rules there, we might say something like this. If the current character is numerical, then take all subsequent numerical characters and create an integer token with them. So here's what an implementation of that might look like in our takeNext function. What we're doing is we're using a switch statement, and we're switching on the current character in our code stream. And we're doing this funny thing. We're saying case is number. And in that case, we're then taking all the characters, subsequent characters matching is number, and we're using them to create a string and using that string to create an integer token. So what is this isNumber thing? That's not something that's built into Swift. Well, isNumber is just a function that takes in a character and returns true or false based on whether that's a digit character. And the reason I'm able to use it here in my switch statement is because I've overloaded the custom pattern matching operator, and I've told Swift that I want to be able to switch on characters like this using functions that I define. So this is, I feel like, an underrated feature in Swift, which is the ability to do custom pattern matching. You can do it with your own types, and you can get more advanced with the way that you unwrap things, and it interacts with those kinds of patterns, and it's pretty powerful, actually. Here I'm using it in a very simple case, but it does help clean up our code a little bit. So this will handle integer literals. Let's expand it. Oh, thank you, SwiftBird. That was good. Let's expand it to handle white space as well. So we'll just add another case to our switch statement, and we'll say case is white space. And here I'm showing you the isWhitespace function. It's nothing remarkable about it, but I'm able to use it in my switch statement again because I overloaded that pattern matching operator. And I'm also doing something else with this function, which is noteworthy, which is that I'm passing it in directly to this take matching function. And that's another one of these niceties of Swift, the ability to use functions as first-class citizens. So the take matching function simply generalizes this, the ability to take each subsequent character that matches this definition and concatenate them and return that string. And I'm able to generalize that instead of writing it over and over again for each character type because I can just pass the function around, which is great. So we've so far been able to handle tokenization by looking at the current character and knowing exactly what kind of token we were dealing with. But it gets a little bit trickier when we start talking about keywords and variables. And that's because loop counter, for example, is a perfectly valid variable name in Bitsy. But if you were looking at the L character, you wouldn't know if you were dealing with a variable name or the loop keyword until you got past the P character. So you could think of solving this problem by peeking ahead, like one character at a time, until you gained enough context to figure out what kind of token you were dealing with. But actually, this is another case where some of Swift's features make our implementation really clean and really nice. So I'm going to define another one of these little functions for my case statement called isIdentifier. And an identifier is going to be a string composed of letters and underscores. And I'm going to take this string, this identifier string, and I'm going to use it to try to initialize a keyword. And if that succeeds, if I get something back, well, I know that I have a keyword, because remember, we made our keyword initializer failable, and we used the backing of that raw enumerated type, that string, to define what valid keywords were. So if this works, I have a keyword, and if it doesn't, then I must have a variable. So it just, again, cleans up our implementation and reduces a lot of duplication that we would have to put logic in multiple places, which is nice. So we now have a tokenizer that handles implementing, that can tokenize white space, integers, keywords, and variables. We've gotten pretty far here. And it turns out we've actually done all the hard work, because the remaining tokens are really simple. So parens and operators are single character tokens. So if you have one of those characters, you just make a token with it, and you're done. And comments are also easy, because if the current character is an open curly brace, we just blindly take all the subsequent characters until we get to a closed curly brace and make a token with those. Pretty straightforward. So we've completed this next step here, which is breaking those characters into our language components. Now we actually have to start thinking about processing those instructions and understanding what the developer is trying to express in their program. So there's a fancy name for this as well, a lot of fancy names in compiler world. This is called parsing. So parsing succeeds if a program is valid, and it fails with an error if the program is invalid, because our tokenizer is just breaking things into these tokens. It's not analyzing in any way whether this is a valid program. You could type in a bunch of nonsense keywords and variable names that don't express a valid program or any kind of instructions in any way. So this is where we start to try to understand what's going on with those instructions. Let's talk about parsing this program. This is the simplest program that you could write in Bitsy. It's called the Bitsy null program. It's just the begin keyword followed by the end keyword. But it's actually a little trickier than that, because it's the begin keyword and the end keyword, but separated by white space, and that white space is arbitrary. So how could we think about this problem here? What I want to do is introduce just a little bit of formal notation. And what that notation is going to do is say that we're defining our program as being equal to the begin keyword, followed by a white space character, followed by 0 or more white space characters, which is what those curly braces connote, followed by the end keyword. And once we have this notation, we can then think about, there's a name for this. It's called the grammar, right? So this notation defines the set of valid programs, another one of these fancy words. And we're going to expand this notation as we expand what we can handle in our parser. But let's start here with this simple case of the Bitsy null program. And let's write a parser that can handle this grammar. So here is a just straight hard-coded version of a parser that will succeed if it gets a valid Bitsy null program and fail otherwise. What I've done is I've used guard statements, and I'm guarding saying if the current token's type is a begin keyword token, then we're good, we can continue. But if it's not, then I want to throw an error out to the user, and I want to cease the compilation process, because this isn't a valid program that we can compile. After I have matched on that begin token, I can then advance over one white space token and any subsequent white space tokens. And finally, I use another guard statement to ensure that my final token is the end keyword. Now, just in this simple example of this parser, we actually see something that's important, which is that our parser implementation follows the shape of our notation. And that's why I introduced the notation, not just as some kind of academic exercise. It's because the notation is actually going to be really useful in defining what our implementation is going to look like. And I think that gets a little bit clearer if we refactor our parser a little bit. So here again is our grammar, and here is a refactored implementation of our parser. So what I've done is I've pulled out those guard statements that match a given token and throw an error into a function called match token type. And I've also pulled out a function called advanced token that internally is going to skip past any white space or comment tokens, because those don't impact the execution of our program in any way. So it turns out that anytime you match on a given token and it succeeds, you're going to want to move on and look at the next token. So we can move our call to advanced token into our call to match. And once we've done that, and we're automatically skipping past this white space, we can actually remove it from our formal notation at the top as well of the grammar, because we don't really have to think about it anymore. There's actually one more step that we can take here, which is to extract our program parsing routine into a program function. And so now we see very clearly that our little parser follows the shape of our tiny grammar perfectly. So let's expand it. Let's handle some more than just the Bitsy null program. Now, in a real Bitsy program, we'll have the begin keyword and the end keyword, and in between, we're going to have any sequence of valid Bitsy statements. And we'll give that a name. We'll say that any sequence of valid Bitsy statements is called a block. And so let's define what a block is formally, and let's start by implementing just one of the valid set of statements that we have in Bitsy. Let's implement the loop. So in our grammar, we'll say that we can have a block, and a block is 0 or more loop statements. Again, that's what the curly braces mean. So now we can define our loop as being the loop keyword, followed by any sequence of valid Bitsy statements, followed by the end keyword. But we just said earlier that any sequence of valid Bitsy statements is called a block. And so that's what we write in our grammar. And something interesting has happened here. Our grammar has become mutually recursive. So blocks can have loops, and loops have a block inside of them. So we have yet another fancy name here. Oh, right. Real quick, we can note that we can now, with this grammar, handle all of these cases. The Bitsy null program still works. We can handle a program with a loop inside of it. We can handle a program with multiple loops, one after the other. But most interestingly, because of that recursive aspect, we can handle loops that are nested, and in fact, arbitrarily nested. So as I was saying, we have a fancy name here. It's called recursive descent. And that just is because our grammar is recursive and because we descend through our source code as we parse it. So how do we implement this grammar, this recursive grammar? Well, let's look at that. There's our grammar again at the top, and here's where we left off with our parser. And when we see this block definition in our grammar, we're going to literally just call out to a block parsing routine, another function. And in our block function, well, we know that blocks are terminated by the end keyword in Bitsy. So until our block function sees an end token, it's just going to keep parsing loops, because loops are the only other valid statement that we have in our language right now. So then our loop parsing function is going to match the loop keyword, parse a block, and match the end keyword. Believe it or not, this is a fully functioning recursive descent parser for this little subset of the Bitsy language that we've defined so far. This works. Now let's expand it a little bit. Let's add the break keyword in here. So we'll say now that blocks can consist of 0 or more loop or break statements. That's what the pipe operator means in our notation. And a break statement is just the break keyword. So now inside of our block parsing routine, we use a switch statement on the current tokens type, and we say, well, if we see a loop keyword, go off and parse a loop, and otherwise go parse a break statement, because that's the only other valid statement in our language right now. So our break parsing function simply matches the break token, the break keyword. And it's interesting here, this is kind of a happy accident. You'll notice that I had to name my break parsing function doBreak instead of just break. And that's because break is also a reserved keyword in Swift. And having implemented our own tokenizer and a bit of our own parser, we can actually understand why that is a limitation that exists in many languages. So imagine for a second if we wanted to allow Bitsy developers to use loop as not only the loop keyword, but also as a variable name. Well, think about our tokenizer and think about how much complexity it would add to that tokenizer to try to figure out the context of where that word was being used to determine whether it was a variable or whether it was a keyword. It would be really difficult, and so we actually just disallow it. We don't allow it, and that's the same trade-off that the Swift compiler authors have made and occurs in many other languages. So it's kind of neat that we can see why that's happening. So far we've been able to determine whether the user is inputting a valid program, but we haven't done anything with that, right? So we'll succeed if the program is valid, we'll fail with an error if they make some kind of error in their code. But we're not doing anything that can run. We're not producing anything useful. So now we get to this step, which is code generation. And code generation just means we want to produce code in the target language, Swift, that has the same effects as those the developer is expressing in the source language. So we'll start just by literally adding print statements into our parser. It's that easy. Obviously, we'll want to do more later, but we can start there and kind of debug this. And when a developer puts the loop keyword in a Bitsy program, they're saying, I want the next block of code to be repeated indefinitely. So we think to ourselves, how would we express in Swift a block of code to be repeated indefinitely? Well, you could use a while true loop. And so when we match a loop token, we're literally just going to print out while true open curly brace. Then we're going to go parse a block, and we're going to assume as we're doing that a bunch of other code is being generated. And then when we come back and match the end keyword, that's the developer saying, this is the end of the block of code that I want to repeat indefinitely. And so in Swift, the equivalent is just a closed curly brace. And we could do the same with our break parsing routine. The semantics here are identical, so we just output the break keyword, and that will exit the while true loop that we just created in our loop function, assuming the developer is using it inside one. So this almost seems like too easy to work, but it does. And I'm going to try to demonstrate that a little bit here. So what we have is, on the left-hand side, I'm going to show our compiler's program stack being built up, right? As our compiler runs, this is the stack of the executing compiler. And then in the middle, I'm going to show with the blue arrow is going to point to the token that's being processed, that's being parsed. And then on the right-hand side, what I'll do is I'll output the code that is being generated. Now, this Bitsy program is totally useless. It doesn't do anything. But it is valid, and so it should compile. And we should be able to produce equally useless Swift code on the other side. So that's our goal here. And this is an animation. It's going to run. You're not going to be able to follow every step. But hopefully, you'll get the idea of how this recursive descent algorithm works. And it's actually pretty neat. And there it goes. So what you see is, as we parse each block, we're dispatching out to other blocks. And those are dispatching out to loop parsing functions. This one's going to dispatch out to a break parsing function. Then it's going to return off the stack. We're going to go back to that other block. And it's going to now go dispatch out to parse the break keyword. And finally, we return all the way back up to our program block. We match the last end token, and we're done. And as we've been going through that, we've generated the Swift code on the right-hand side. And if we look at that, that code is equivalent and equivalently useless to our Bitsy program. So it worked, which I think is pretty neat. Now, I do have a confession for you guys, which is that the loop statement in Bitsy and the break keyword are intentionally designed to be really like good places to start with implementing recursive descent, right? They're kind of the easiest case that you can imagine. And the semantics line up really well with Swift. So the code generation process is really easy. Now, it does get more difficult as you go to implement more difficult statements, and you have what I would call semantic mismatch. And I want to give you just a couple of tastes of that, right? We're not going to have time to implement anything else here, but we can look at how this gets a little bit more complicated. And the reason we're going to look at it is because I don't want you guys to think that I'm like pulling a fast one on you. So you've seen how it works, right? You've seen the base simplest case, and it gets more complicated, but it works the same way. We're just tackling some programming challenges at that point. So let's take a look at how we might generate code for this assignment statement in Bitsy. We're just saying foo is equal to 10, right? Well, your first thought might be, well, I can just say var foo equals 10, right? That's the equivalent Swift code. I could generate that. But if the developer's next line or somewhere else in their program was to assign another value to foo, and then you generated this code, Well, that's a problem. When you go to compile your Swift code, you're going to get an error. You've redeclared foo. So we can't just have this one-to-one translation the way that we did with the loop and the break statements. So this is because Bitsy variables and Swift variables actually have pretty different semantics. So Bitsy variables are global. They're not scoped to the block. They don't require any declarations, and they're initialized automatically to 0. But Swift variables are scoped to the block that they're declared in. That declaration is required, and you have to provide an explicit value for them when you declare them. So how do we handle this? Now, when you might be tempted to say, well, let's just not have any semantic mismatches in our language. But when you're writing a compiler, you're pretty much always going to have these. If the semantics of the language you were implementing were identical to the language that you're generating the code for, there probably wouldn't be a great reason for your new language to exist, right? You're always going to be trying to do something that semantically is a little tough in the language you're generating the code for. So there are a few options that we have here. We could, for example, add a variable scanning phase to our compiler. So we could, before we did any other parsing, we could look through our whole Bitsy program and we could say, where are they using any variables and what are all those variables? And then we could generate at the top of our outputted Swift code declaration statements where we said var foo equals 0, var bar equals 0, right? And then that would work. That would set up the semantics the way we were expecting. But it adds complexity because now we have this additional phase to our compiler that we have to write. We could also try to add state to our code generation routine, right? So as we're parsing, we're maintaining where we are, like when we've seen a variable or when we haven't seen a variable, whether we've declared it or not, and then try to output different code based on what's going on rather than just having a clean one-to-one mapping. But again, that could work. It's going to add complexity. The third option, and this is the one that I chose, was to just generate less literal, less efficient Swift, but Swift that had the same effects as the semantics I was expecting in Bitsy itself. So what do I mean by that? Well, what I did was I implemented this little struct called variables. And what variables does is internally it just has a dictionary of strings pointing in integers. And it implements custom subscripts where you can get at the values of those, you can put in a key and get the value back. But if the key isn't there, instead of returning nil, instead of returning an optional, it always returns an int. And if the key isn't there, it returns a 0. So then at the top of every program that I compile from Bitsy into Swift, I just plop this code at the top, and I declare this variable's hash. And then, when I'm parsing some statements like this, I can just output code like this, and this works. This gets me the effects that I need. And in fact, if the developer goes and assigns bar to foo, but bar hasn't been assigned any value anywhere in our code, well, I can just translate that straight up, and this still works, because my little hash is going to do the inefficient lookup, but it's going to work and give me back 0, which is what I was expecting. So the point here is that it does get more difficult. You're going to have to find ways to resolve these semantic problems. You're going to have to generate less literal, more mechanistic code. You're going to have to use in your code that you're generating the token values that you carried forward. But all of these things, hopefully, don't seem magical. They just seem like programming challenges, things that we would have to hack on and work through, but we could imagine getting working. So some other things to think about: how do we generalize and extract code generation? How do we parse more complex statements? Like the conditional statement has an optional else branch. How do we deal with that? How do we define a grammar that handles operator precedence? This is an interesting one, right? So we have these rules about mathematical operators and how they execute. I would have loved to have talked about how you do that, but there just wasn't a ton of time. There's also even some undefined behavior, even in our little Bitsy language. So what happens if the developer puts a break keyword outside of a loop statement? How does our compiler deal with that? We haven't talked about that. So again, all of these are not necessarily trivial, but hopefully they don't seem like magic. Hopefully they seem like interesting challenges that are fun to hack through. So we've gotten all the way to the point where we're now generating instructions in our target language. And we want to output those instructions into a file. Our Swift code has to go into a file, and we have to shell out to the Swift compiler itself to compile that file down into a binary that the user can actually execute. So they can write Bitsy code and get a binary that will do what their Bitsy code said. And that turns out to be our second Stack Overflowable problem of the day. And so with that, we've completed the process of implementing a simple compiler in Swift. Now, if your interest has been piqued here and you want to learn more or see a little bit more about what I was doing, I'll point you toward a couple of repos. There's the Bitsy Swift repo, which is the fully implemented Bitsy compiler in Swift. I just updated it for Swift 3.0. And so that's where I was pulling these code samples from that have been in my slides, and if you want to take a look at that. There's also Bitsy Spec, which I mentioned earlier. It's a series of unit tests that if you're implementing a Bitsy compiler or interpreter in any language, you can point this command line utility at your implementation and see what works and what doesn't. One other resource I'll point to specifically is this paper from this guy named Jack Crenshaw in the 80s. It's called Let's Build a Compiler. It's really great because a lot of the resources out there for learning this stuff, and this is part of why I wanted to do this talk, they're very opaque. And they start with all this theory, like let's derive how regular expressions work from set theory or something, and it's like, oh my god. And it doesn't actually have to be like that. And this paper was where things really started to click for me because he gets right into the practical stuff. Like here's tokenization, here's parsing. Like you can do it with a simple language, and he really walks you through it, and it's pretty cool. If you also check out the README, or in either of those repos, I have a resources section where I point to what I think are some other good resources for getting started that are approachable and were helpful for me. So one favor that I ask for you, if you like this talk, if you're interested in this stuff at all, I am hoping that this little Bitsy project may actually be useful to other people, even outside of our own community who are interested in language implementation. Like I think it would be really neat if there were like tutorials in different languages for how to implement a Bitsy compiler, and it makes a good place to start. So if you can spare a couple of GitHub stars on those repos, it really does help with discoverability for the projects and lend some credence to them. So that's it. I don't know if we're doing questions or if there's time for questions, but you can always talk to me at the rest of the conference. Everyone probably wants to get to lunch. You can also find me on the internet at these places. So thank you. Any questions? I will take questions if there are any, but people want to eat. All right, well, thanks, you guys.
So Angela ran out for a minute. I'm going to try and do this emceeing. She does it a whole lot better than I do. Ben did a great job, yeah? Very good. So it looks like lunch is at 12. I don't even know what time it is now. Does anyone know what time it is? 11:33. So you're welcome to hang out here and then do what you want. Head down for lunch at the gazebo at 12 and running a little ahead of schedule. You guys probably need a break after yesterday's pretty day. So that's no I'm for. So we'll see you guys down lunch.